Today, we are going to build a multi-layer perceptron from scratch using Python. We will work with an input shape of 500 by 4, meaning we have 500 samples, each with 4 features. Our architecture will consist of input layer, 4 features, 2 hidden layers, the first with 10 neurons and the second with 6 neurons. Both will use rectified linear unit as the activation function. Output layer, a single neuron using a sigmoid activation function, as we are performing a binary classification task. First, let's create our helper functions. Number 1, rectified linear unit activation. This returns the input value if it is positive and 0 otherwise. Second, rectified linear unit derivative. This returns 1 if the input is positive and 0 if it is negative. It acts as a gatekeeper during backpropagation. Third, sigmoid activation, used at the final layer. Finally, binary cross-entropy loss. We include a small epsilon term here to prevent log0 errors, which would otherwise cause numerical instability. Note, we aren't writing separate derivative functions for the sigmoid and loss functions. When combined, their derivative simplifies to a very elegant equation. This allows us to bypass the more complex calculus while maintaining perfect accuracy. Before we code the class, let's establish the rules for the shapes of our weights and biases. Weight matrix rule. The shape is neurons in previous layer, neurons in current layer. Bias shape rule. The shape is 1, neurons in current layer. Following these rules, W1 is 4, 10, B1 is 1, 10, W2 is 10, 6, B2 is 1, 6, 3 is 6, 1, B3 is 1, 1. The forward pass is straightforward. We compute Z1, apply rectified linear unit function to get A1, and pass that into the second layer. We repeat this to get Z2 and A2. Finally, we compute Z3 and apply the sigmoid function to get our final prediction, A3. In backpropagation, we calculate the derivative of the loss with respect to every weight and bias. Let's start with the output layer W3. By applying the chain rule, we know that W3 affects Z3, Z3 affects A3, and A3 affects the loss. Normally, you would multiply the derivative of loss with respect to A3 by the derivative of A3 with respect to Z3. However, as mentioned earlier, this simplifies beautifully. When we compute the derivative of loss with respect to A3, we get this. And when we compute the derivative of the sigmoid function A3 with respect to Z3, we get this. Finally, when we multiply both the derivatives, we get the simplified equation A3 minus y. This is basically derivative of loss with respect to Z3. To find the gradient for W3, we take the dot product of the previous layer's output A2 with dZ3. For the bias B3, the derivative of Z3 with respect to B3 is simply 1, so the gradient is just dZ3. Now we move backward to the second hidden layer and compute the derivative of loss with respect to W2. We compute dA2 by taking the dot product of dZ3 and W3 transposed. To find dZ2, we multiply dA2 by the rectified linear unit derivative. This ensures we only pass the gradient through neurons that were active during the forward pass. We then follow the same steps to find the gradients for W2, B2, W1, and B1. Finally, we implement the train function, which calls the forward and backward passes in each epoch and updates the weights using a learning rate. We also add a predict function to generate outputs for new data. To test our model, we will use scikit-learn's make classification to generate a synthetic dataset, split it into training and testing sets, and watch our MLP learn. This is a multi-layer perceptron built from scratch. I hope this breakdown helps you understand the inner workings of neural networks. For the complete code, check out the description and let me know in the comments what you'd like to see covered next.